welcome to statistical learning session. Today we'll be continuing the chi-square test. Last time we talked about disjoint Gaussian. So this n square root and p minus p naught is asymptotically normal or is asymptotically Gaussian. That's what we are saying here. And what we're going to tell you is that if I multiply this square root n and inverse of Fisher information, not inverse, but square root of Fisher information multiplied by p, p hat, p naught, then in the asymptotically it should be a normal distribution with a k suffix and zero mean and identity k. This should be ideal condition, and this is not going to be the case. Do you know why? This is not going to be the case because what we know is that this is z. Now for example, let's take that this z is something like nk and 0 ik. Let's assign this as a z. And if we multiply z transpose with a unit square, a unit vector, then it's supposed to be 0. But it will not be 0 because z is not a p. Z is not like this. It's not going to be like this because z is not this. If z was this, then it could be possible because we already know here, right? If z was this, then it is equal to 0, but z is not that. That's why it is not equal to 0, and hence this is not a true case. So what happens then? What we know is that if we do this, then let's say this is a three-dimensional space and this is a unit vector here. Z square, the z lives in the two-dimensional space in this space. So it's going to be a one less dimension where the z square lives or z vector lives. Now what we have here is this is a left hand side of this equation where this is a square norm of p minus p naught, and this is square norm, and this is supposed to give us a square Gaussian. And square, by definition of wall test, square Gaussian is a chi-square. Now, why it is not k dimension? Why it is k minus 1 dimension? Can you tell me? It is like that because this chi-square also lives in k minus 1 dimension, as in z, because in a last dimension what we have is a unit vector, and because of that this chi-square is k minus 1 dimension, and in a last vector there's no variability, and that's why we have to take it out from our calculation, and because of that this is k minus 1. As we move on, we also can say that let's create an equation here. What we need is a square root of n and p. If everything was good, then it should be limit should be n to infinity nk and 0 I minus 1 p naught. This should be the case if it was ideal case, and also it should be I inverse p naught and unit vector equal to 0. But this is not the case. Why is that? Because there is no I inverse here. We don't have any I inverse because there's no variability in the I vector in I dimension, and because of that, what we did do is that this is a pseudo inverse of that. We don't have I inverse, but what we have is a pseudo inverse. Because of that, we have instead of -1, it is just t pseudo inverse of that. And also, what we have is instead of I minus 1, we have a pseudo inverse of that. Therefore, there's no real thing going on here. So, beside that mitigation for a unit vector, all the calculations remain the same. So, let me briefly recap what we learned today. What we learned is that we learned about chi-square test, and chi-square test lives in the not in full k dimension but k minus 1 dimension, because pj minus p does not live in k dimension but lives in k minus 1 dimension. And why is that? It is that because the last vector, the last dimension, is a unit vector where there is no variability, and because of that we have a one less vector or one less dimension than our full dimension, and that's the reason why we have a k minus 1. So that's all for today. I'll see you next learning session. Thank you so much.